All right, folks, here we are with Winter 21. This is an SL question, and it's from paper 2, and we're looking at question 4 here. Okay. This question is about a combination of electricity and magnetism. Okay, so again, I think we'll do our usual thing of just scrolling through and making sure we're at the right points and finding that stuff. There we go. We're looking at our electric fields. Okay, we've got a few equations there. Some of this, you never know, might be useful. Okay, let's go for it. We're told the work done to move a particle of charge 0.25 microcoulombs from one point to an electric field to another is 4.5 joules. So immediately we're looking at work and charge, and we're being asked to calculate the magnitude of a potential difference. Okay, well, I would suggest we get looking in the data booklet. We scroll down here. Here we go. Here's our equation V, potential difference W over Q. We've got work, we've got charge. It's a 1-mark question. Should be fairly simple. Okay, all we're going to do there is put in our values. Now you notice here we've got micro, and these are going to nicely cancel. I've put them in green, but you wouldn't have to necessarily have them in there. Okay, as you can see in the mark scheme, you can get away with not including those multipliers in there. You might want to put them in just to help yourself out. Okay, and we've got 18 joules per coulomb or 18 volts. Now, the standard unit for voltage is volts, so why not give it that way as well? However, it's worth knowing that 1 volt is 1 joule per coulomb. Okay, now we've got a charged particle P with a large charge, 68 microcoulombs, and a second one with a small charge, 0.25 microcoulombs, held at a distance 48 centimeters. Now notice here there's a lot of prefixes, 10 to the powers of -6 and 2, and we are going to have to include them in our answer this time. To calculate this, we're going to use Coulomb's law, which is F is equal to KQ over R squared, or 1 over 4 pi epsilon naught, then times QQ over R squared. Either is okay. Okay, we're going to put in our numbers now. We've got to be careful. We've got our K, which is 8.99 times 10 to the 9. We've got our Q, which this time is 68 microcoulombs, 10 to the -6, times 0.25 microcoulombs, 10 to the -6 again. We've then got 48 times 10 to the -2. Okay, and we're going to have to square that. That's a common thing that we forget, and we're going to get our answer 0.66 newtons. Now, very important that if we look at the mark scheme here, okay, it says we do not allow error carried forward for incorrect or not squared distances. Okay, so they're going to be a bit nasty here. All right, it means if you forget to include, if you forget to carry forward that, you forget to put in the right distance, or you forget to square it, then you may lose 1 or even 2 marks here. Okay, so something to pay attention to. Make sure we're squaring when we're using KQQ over R squared. We're going to make sure that we do all the operations, even though there's a lot going on here. All right, describe the motion. We're going to let Q go, and we're going to think about what happens. Well, obviously, these two guys are positively charged. All right, and therefore, Q is going to move away from P. Now, if you notice here, I wonder if I'm going to lose a mark here, all right, because we do need to have the idea that we're moving along a straight line. Okay, initially I said Q will move away from P, okay, and I said that there's repulsion between the two. I think I'm probably going to get the mark just about because I've said that they're repelling each other. Okay, now obviously the speed is going to increase. Okay, we experience a force, we're going to have an acceleration. However, when I wrote this answer, I said we're going to have a decreasing acceleration. And the reason for that is because the force is decreasing. Now, if you notice in this kind of question, we actually have multiple points you could get. Okay, you could say that it moves away along a straight line, or that they're repelled. Okay, it repels with increasing speed. Okay, obviously acceleration, but that acceleration also decreases. Okay, you may have written an answer that gets all 3 marks, and that's absolutely fantastic. Okay, we then switch the focus from electric fields to magnetic ones. And this seems to be the one that my students have struggled with in the past. Okay, now I'm going to apologize at this stage for my dreadful drawings. I did this really quickly because this is a response to a student question, so please forgive. All right, we're looking here at 2 parallel wires X and Y, and it's really important that we remember our right-hand rule at this stage. We have 2 parallel wires carrying currents into the page. And what that means is that we're going to get, due to that wire X, we're going to get a clockwise, or due to both of them actually, sorry, we're going to get a clockwise field. And we're interested eventually in how these guys add together, but we're going to take our time over that. We're first asked to add on the diagram an arrow to show the direction of the magnetic field at Q due to wire X alone. Wire X has its own magnetic field, and we want to know the direction of that field. Well, it's a circular field. I'm aware this is a dreadful circle, okay? But the bit that we are interested in is the one I've drawn quite well. You notice here that, say, an angle of 0, okay, we've got a field to the right. At an angle of 90 degrees, where we've got a field down, and halfway in between is 45, we've got a field which is actually somewhere in between, okay? We're pointing diagonally down to the right. And if we carried along that line, we would have fields at every point acting diagonally down to the right. And this is because it's a circular field due to wire X. Okay, so this arrow that we should draw, okay, should look something like what they've drawn in the mark scheme, okay, and you can have an arrow of any length. I've drawn a fairly short one, they've drawn a long one, doesn't matter. Now, the last bit that we need to talk about is the magnitude and direction of the resultant magnetic field. Now, we've got two magnetic fields here, all right, one which is pushing down and to the right due to X, and then we've got Y. Now, we follow the same logic. If we're at Y, we follow along this line. Well, if we were at 0 degrees, we'd be pointing up. 90 degrees, we'd be pointing to the right. So halfway between the two is up and right. Okay, so we've got a field along this point at point Q, which is going to be pointing up and to the right. We're now adding two vectors together, and those two vectors are clearly at right angles to one another. Okay, they're going to add together, just as I've added my triangle here, to make B, I've called it BX, the field due to X, plus the field due to Y, BY, is going to make BT, which is the total. Now, each one of these, we are told somewhere, here we go, has got a field value of magnetic field strength of 15 millitesla, not mega, that'd be huge. Okay, and so therefore, actually, if we want to know BT, the size of the total field strength, we're going to take BT squared equal BX squared plus BY squared, which is 15 squared plus 15 squared is equal to 450. And we're also going to remember to square root it. Now, we notice in the question, it tells us we want to know the magnitude. That's one mark there, which is 21 millitesla. Okay, but we also got to remember to state the direction, and we've got to say something to the right. Now, the question would be, would you get the mark if you just did the drawing? I wouldn't be so sure. If the question asks you to determine the direction, make sure you state it somewhere explicitly. It's worth it to get that extra mark, which could be the difference between a 5 and a 6, or maybe even a 6 and a 7. All right, I hope that was helpful. Thank you very much for watching, and if you've got any questions, please don't hesitate to ask.